This is a question on antennas, and the question is here. The far zone power density radiated by a helical antenna is approximated as W rad, and the radiated power density is symmetrical with respect to phi and exists only in the upper hemisphere. C naught is a constant, the power radiated by the antenna in watts, and the maximum directivity of the antenna respectively are. So, we have to find the power radiated by the antenna, the total power, and also the maximum directivity of the antenna. So, let me just draw a schematic here. So, the schematic is like a sphere. So, it says that the azimuth phi is symmetrical for 0 to 2 pi, whereas for theta, which is varying from 0 to pi by 2, and the expression for the power which is radiated is given like this. So, this is, as you know from previous problem solving sessions, that W rad is the Poynting vector for the electromagnetic field. So, this is in watts per meter square. So, this is the power which is present at the surface of the sphere, and we have to find the total power which is radiated by this antenna. So, to find the total power radiated by this antenna, what we can do is, let us say, power total. We can what we can do, similar to the Poynting vector, is to integrate surface integrate this half a sphere, surface integral of this vector, which is W rad, which is the average power density, which is dot product with a small area Ws, and this value, if we solve this value, it gives us the total power radiated by this antenna. So, let me just go ahead and solve this integral. So, what we know is the surface integral of our sphere can be written like this. So, phi is varying from 0 to phi is varying from 2 pi, and theta is varying from 0 to pi by 2. We have W rad, which is given by W rad, and ds, which is the small elemental area on this sphere, surface of the sphere. This we know that ds is given as r sin theta d phi, and r d theta, which is given as r square sin theta d theta d phi. So, ds is r square sin theta d theta d phi, and the vector here is ar, since the surface is pointing outwards in the radial direction. So, this is a dot product between these two, that means the vector ar and ar will come to be 1. So, what we have is P total is equal to, so it is 0 to 2 pi and theta varying from 0 to pi by 2, C naught upon r square cos 4 theta, and we have r square sin theta d theta d phi. Now, we cancel these r square and r square, and C naught is a constant which will come out. So, this is given as C naught 0 to 2 pi d phi and 0 to pi by 2 cos 4 of theta sin theta d theta. So, this amounts to P total is equal to C naught into 2 pi, and this integral we have to solve. We have to solve this integral by substituting cos theta equal to x. So, if I substitute cos, so let me just do a small rough work here. So cos theta equal to x. So if you differentiate this, so it's minus sin theta d theta equal to dx. So if you substitute in this, so 0 to pi by 2. So once we substitute, we'll change the values of the limit. So it's x raised to 4 minus sin theta d theta, and these limits will change from, since theta is equal to 0 is 1 and it will go to 0. So x raised to 5 is x raised to 5, sorry, this is not it's just dx. So it's x raised to 5 upon 5 and the limits are varying from 1 to 0. So if you solve this, you will just get 1 by 5. So it's 1 by 5. So you get 2 pi by 5 C naught, which is equal to 1.256 C naught. So this is the total power radiated by this antenna, and since in the answer we have B and C which has this value, then we have to go to the next part where they are asking for the maximum directivity of this antenna. So let's just calculate the maximum directivity for this question. So the directivity of an antenna is given by, so let's just say if D is the directivity which is varying in theta and phi, it is given by radiation intensity that is varying in theta and phi divided by power per steradian. So in this problem which we have just now, so the total power, we know the total power is P total is equal to 2 pi by 5 C naught. This is from the previous solution, and we know that the total we have to find the total power per steradian. In this case, this is steradian is for a omnidirectional antenna, that is a sphere, and the total steradian that a sphere that a point extends over a sphere is given by 4 pi. So power per steradian in this case, so power per steradian in this case is P total by 4 pi. This is the solid angle extended by a point over all the sphere for a omnidirectional antenna. So this gives 2 pi by 2 pi C naught by 5 into 4 pi, and we can just solve it like this. So it's C naught by 10. So this pi is there, and it's 2, and it's C naught by 10. So we now the denominator of this part, now we have to find the radiation intensity. So the radiation intensity can be found out by checking what is the units of this one. So the units for this one is the amount of power in each steradian. So in this case, what we can do is to find this value, we can write radiation intensity also as U of theta phi divided. So radiation intensity can be also written U of theta phi. So let's just say U of theta phi is equal to the radiation intensity U of theta phi can be written as the total power per steradian. So that is total power per solid angle, the incremental total power divided by the solid angle for that antenna. So this, so the incremental solid angle can also be written as d p total divided by dA by r square. So, it is r square dP total divided by elemental area. So, this is a relation that you have to remember, that the solid angle d omega is equal to the angle subtended divided by r square. So, this is one of the most important things you have to remember while solving this problem. So, now we know that u of phi is given as this, and this expression here is nothing but, so u of theta phi equal to r square dP total by dA. This is nothing but r square, this is the watt per meter square for this thing, and it is actually the again the Poynting vector, which is already known. So, it is given in the question. So, now we find the directivity. So, d theta of phi is equal to r square. We put the magnitude of this. So, it is just the magnitude of this part. So, it is C naught by r square cos 4 of theta divided by C naught by 10. So, this is gone. So, this is just 10 cos 4 of theta. Now, the question asks for the maximum directivity. So, the maximum directivity occurs when theta is 0. So, d max is theta equal to 0, but in the phi it is symmetrical. So, for theta equal to 0 we have 10, and we have to convert it into dB. So, we will just do that. So, it is just d max 10 log 10 of d max equal to 10 dB. So, this is the answer. So, once we check the question again, so what we have here is the option B, which is the correct option, which says that the total power emitted by this helical antenna is 1.256 C naught, and the maximum directivity of this antenna is 10 dB. Thanks for watching. Please subscribe to our channel for more such problems, and also check out the books that I recommend in the description.